In this example, I'm going to be looking at a set of capacitors that is a little bit more complicated than some of the previous examples. In this case, we have kind of series and parallel happening simultaneously. Looking at this, when I first approach a problem like this, what I try to recognize is what I can say about the relationship of different capacitors with one another. For instance, I can see that capacitor number 1 here is sort of in series if I follow the wire with number 2 and number 3, but on a different pathway it's in series with number 4, because I can trace a line through both of those. That's a problem, that it's in series with these two, and it's kind of in series with this fourth one, but they're not all in series, so I can't really do much with C1 right now because of that, because it kind of has relationships with two different sets of capacitors. Likewise, when I look at this little box here, this tells me that there's something parallel going on in this circuit, and I can see that on this side there's a connection, and on this side there's a connection. But if I look at the individual capacitors, I can see that capacitor number 4 is not completely in parallel with number 2, because while it shares connections on this side of it, capacitor number 4 on the opposite side of the capacitor does not have a direct connection to C2. Instead, it runs into C3. Then I'm left with kind of one set left, and I can see that C2 and C3, they do have just a straight line connection, and so I would call those two capacitors in series. And so I'm going to start by just drawing a little arrow here to designate that I'm going to combine these two things in series. And I'll just write that out, series. That's going to remind me later on what the heck it was that I did. So I'm going to say C2 and C3. And now what I'm going to do is just redraw the whole circuit. And it gets a little tedious sometimes, I get that, but it's a good practice to get into redrawing your circuit. And the reason for that is because we want to stay as organized as possible with the information as we start solving things. If you just skip kind of to the end, it's very easy to run into trouble with staying organized with your numbers. So what I've done now is I've combined C2 and C3 into one equivalent capacitor. Finish drawing this. And it's okay that my circuit's a little bit smaller. Again, all the connections are the same, so that's really what matters. So up here, I still have C1. Over here now, I have kind of the combination of 2 and 3. Put like a little comma there, just to remind myself that this is C2 and C3 now kind of combined, and this is C4. I realized suddenly that I did not give the starting information for these, so let me do that. This is 6 farads, and this one here is 10. Sorry about that. That would have been a really hard problem to do without that information. So in any case, to combine these two things in series, I have to do some math. I'm just going to do that over here. So the equivalent capacitance for two things that are in series, I have to do the 1 over equation. I'm going to do 1 over 3 plus 1 over 6. And doing that math, type it into your calculator, you should end up with 2 farads. So the combination of C2 and C3 gives you 2 farads. C1 is 8, C4 is still 10. And there we go. I've kind of consolidated it now from 4 capacitors down to 3. I still can't get to, filling in all the Q values and V values because I still have 3 C values, which is too many. I can't plug that into C equals Q over V with 3 different C values. So my next step now is to combine these. And again, I look at C1 and I can see that it's got a shared path with C2/3, but it also has kind of a series path with C4. So C1 is still not really accessible because it has kind of a relationship with both of these, but differently. Probably have identified it by now, but if you look at C2/3 and C4, they have a shared connection on this side, they have a shared connection on that side, which means that they are in parallel. And so what I'm going to do is I'm going to draw an arrow down this way, and I'm going to write out parallel, and that is C2, 3, and C4. And the equation for parallel circuits, if we go ahead and find the equivalent capacitance, it's just the sum of the capacitance values, and so I get C23, which was 2 farads, plus the capacitance of C4, which is 10. Get the calculator out for that one. I get 12 farads. And now what I'm going to do is just redraw this again. 9-volt battery. Capacitor 1 is still there, it's unchanged. But now C2, 3, and C4 have been combined. And I have one capacitor, which is like C2 to 4. And it's 12 farads. The exact naming of this is not really the most important thing. The only reason why I do it this way is just to remind myself what this actually represents. This one is still 8 farads. Okay, and I have ended up with 2 capacitors now. Still, I have a 9-volt battery, but I still can't get down to the final answer here because, again, I want to use the equation C equals Q over V, and right now I have 2 values for C. I have 1 voltage, but I can't actually say that the voltage is 9 across each of these. In fact, I know it's not because I know that when I take one loop around a circuit, the sum of the voltages should be 9. So I am going to combine these two now one more time, and in this case I'm identifying it as series, and the way that I know that it's series is because if I leave the battery and I trace a path, I have to go through both of these capacitors before I get back to the battery. It's only one loop, so these things must be in series. So I'm going to write out again series, and that is C1 and C2 through 4. These two in combination. So now one last drawing. 9 volts, 1 capacitor, and it's the full combined capacitor. To get its C value, I have to do the equivalent capacitance of 1 over, it's this equation again because they're in series. I do 1 over 8 plus 1 over 12. And when I type that into my calculator, I get 4.8 farads. All right, so we get an overall capacitance of 4.8 farads. At this point, I can start filling in some of my other information. So for instance, I can find what the overall charge is because I know the voltage across this capacitor must be 9 volts. Because if we were to look at the two sides of this capacitor, if you somehow made a jump from one side to the other, you're essentially now making the jump across the terminals of the battery, which is defined as 9 volts by this battery. So I have 9 volts and I have 4.8 farads. I'm going to solve for Q using this equation over here. Q equals C times V. So multiplying 9 by 4.8, and I get 43.2. I'm just going to call it 43 coulombs. And now I have the charge, which I now am going to be able to use one of these pieces of information to start filling in information from my previous drawing. So in a capacitor problem, what I do is I start by looking at my full diagram, and here's all the things I need to find. I start breaking it down and getting it smaller and smaller, consolidating my capacitors together until I get to this end point where I only have one capacitor. And now I can actually start filling in some of the details about that, about what kind of charge is stored on it, how much voltage is across it. And what I'm going to do is piece by piece, I'm going to bring those things back with me. Because in this case, what I did to end up with one final capacitor was I combined 2 capacitors in series. And as we know, in series, capacitors all have the same charge, which means that what I can bring back with me is this charge value, 43 coulombs. And so I know that these 2 capacitors each had a charge of 43 coulombs. So C1 has a charge of 43 coulombs. And now that I know that the charge is 43 for both of these, and I know the capacitance values for each of these, I can actually find the voltages. So I can find V1, and I can find the voltage of this combined capacitor. And I can do that because, looking back at this equation, voltage is Q over C. So if I take 43 and I divide that by 12, I end up with about 3.6 volts here. And if I take 43 divided by 8, I end up with 5.4 volts. At this point, I can actually start checking my work, and I can do that because when I do one lap around this circuit, I know that my voltage needs to add up to 9, and so I go through this capacitor 3.6 plus 5.4, and sure enough, that adds up to 9. So I'm pretty sure at this point that we're on the right track. Um, C1 is actually finished now. As you notice, we have C1, we have Q1, and V1, so I can just go back to my original drawing and just fill in that information rather than continuing to worry about C1 in every step of the way. So I have 43 coulombs and I have 5.4 volts. All right, going back to this combined 2 to 4, looking at this, this was two things that were combined in parallel, and therefore, as we know, capacitors in parallel all have the same voltage. Therefore, I know that for capacitor number 4, the voltage is 3.6 volts, and same thing for the combined 2, 3. The voltage here is 3.6 volts. Knowing this now, I know the capacitance and I know the voltage, so I can solve for charge, which again, charge is capacitance times voltage. So I'm going to do that for each of these. So 3.6 multiplied by 2 gives me 7.2 coulombs, and 3.6 multiplied by 10 gives me 36 coulombs. So at this point now, I have C4 also figured out, 36 coulombs, and a voltage of 3.6. Now it's just a matter of taking my combined C2 and C3 and splitting that back up and reminding myself what it was I did. I combined C2 and C3 in series. And so I have to think, well, what stays the same in series? Charge does. So my 7.2 coulombs comes back here to both of these, 7.2 coulombs and 7.2 coulombs. And now it's just one last step to find the voltage for each of these. I go back, I look at voltage is Q over C. So for capacitor number 2, it's going to be Q 7.2 divided by 3. 7.2 divided by 3 gives me 2.4 volts. And 7.2 divided by 6 is 1.2 volts, which is actually what I expected. And the reason why I expected that is because, again, if I complete one lap around this circuit, we have to remember here I can go left or I can go right. I can't go both. So if we follow the path around this circuit and I go to the right, I say 3.6 volts plus 5.4 volts, that adds up to 9. Or if I go around and this time we go to the left, I say 2.4, whoops, I go to the left, I say 1.2 plus 2.4 for this capacitor, that's 3.6, and now I add 5.4 and I get back to 9. So again, just as if you follow the path around a circuit, your voltages should add up to the same amount that's on your battery. If they don't, well, then you kind of have to analyze it a little bit more. If I got like 9.1, then probably it's a rounding thing, and somewhere because of significant figures or some other factor on the problem, you ended up with just slightly different numbers. That's usually okay. But if I ended up with like 12 volts or 37 volts or 182, then probably something went wrong. And a common mistake that happens in these problems, because there's so many steps, is that maybe back here when I was saying that these are in series, maybe I accidentally took the voltage and made that the same for the two instead of the charge. Something like that. It's a simple mistake, but unfortunately it kind of throws off all your numbers. So you do have to be careful, and that's why it's a big deal to stay organized with these problems, and that's why we do each individual step, even though it seems a little bit redundant or it seems like a little bit extra work. We do the individual redrawings and we write out when we're marking things in series or parallel, just so that we can stay organized and so that we can check our work and so that we minimize the chance for mistakes. So that is how we take a circuit that is a little bit more complicated with series and parallel, and we combine the capacitors to find all the information for each individual one.